I'm going to talk about some new techniques. I guess they're about maybe a little more than a year old now, for solving non-smooth stochastic optimization problems. This is joint work with Peter Bartlett and Martin Wainwright, both faculty here. Right, so I guess just before I start, I want to sort of make like sort of a philosophical statement about solving statistical problems. One is the number of data points n, that's my number of sort of samples I have available, goes up. My performance should always increase if I'm solving a statistical problem, right? Even with a fixed amount of computation. And my other thing is that as sort of the number of processors I have goes up. As sort of my amount of computational ability goes up, my performance should always get better. I mean, you know, I could always just throw away data if I can't handle it computationally. So I should always be able to improve when I get more of one resource or another. But that hasn't always been the case in a lot of work. So what I'm going to do today is kind of deal with the second point, which is I'm going to talk about sort of how we parallelize stochastic optimization and different learning algorithms. And some of the techniques I show, these randomization techniques, are going to allow us to parallelize sort of previously, I say impossible, we didn't know how to parallelize these things before. Yeah, so I'm going to start off by just describing my problem, giving a couple examples to hopefully motivate what's going on, and then I'll talk about the algorithms that we develop, and then I'll show how to make them distributed and how they can work in sort of parallel computational settings, and then I'm going to finish up with a couple experiments, just sort of showing what they do. Okay, so the sort of smallest description I can give is that I want to solve the following problem, which is to minimize a function subject to some constraints on a parameter vector W. But in my case, in the problems I care about, I'm going to say that the function f is either some kind of empirical expectation, an average of a lot of different functions on data xi, or it's just some expectation of some loss, capital F, where I'm getting samples x from some distribution I don't know. You know, they could be coming in streaming, I could be Google, and I keep getting searches, and each search gives me a little bit of data when somebody clicks on something. So this is the setup. So a few examples. One would be sort of text classification, right? We have documents. We want to decide whether a document is about sports or economics or technology or government or medicine, something like that. Another example that I think is kind of neat is protein structure prediction. So in this, we're given basically we're given a protein, which is a list of amino acids, and we want to figure out what the structure of that protein is. Because doing that can sort of tell us how it's going to interact with drugs, things like that. And one thing that helps us be able to predict protein structures is if there is one amino acid called a cysteine. And if we can tell, and cysteines bond with each other, and if we can tell which ones are bonded together, then we can more accurately predict the structures of these proteins. So this is another kind of prediction problem that we might want to solve, where the data is basically these strings of amino acids. Another one, parsing. You know, this is really useful for, say, like machine translation and things like that. We're given a sentence, the man took the book. We want to fit it into a parse tree. So our data is sort of the man took the book. What we want to do is predict kind of the optimal parse, separate a sentence into its noun phrase, its verb phrase, and its other constituents. So how do we formulate these as problems, as stochastic sort of or statistical optimization problems? That's kind of our goal in the next couple of slides, is just to construct a loss that measures our performance on these different tasks. So, simple example, text classification. We basically set x to be a vector with 1s for all the words that appear in the sentence and 0s elsewhere. And we get y as kind of the label. And we want to learn weights, our weight vector w, so that the inner product of w and x has the same sign as the label. And so the loss function there is what we've been seeing is this hinge loss, the SVM. So basically what we're saying is we want w.x to have the same sign as y, and you get penalized for being sort of more wrong. So that's a simple example. A slightly more complicated one. So protein structure prediction, what we're going to do is we say, okay, there's a complete graph over all of the cysteines in our protein. Those are the amino acids. And we want to predict the edges. We want to find sort of a matching in this graph that's somehow maximal. So we're going to assign features to edges, which are something like, say, the neighborhood of the cysteine or different kind of chemical properties of the protein. And we want to assign weights so that when we take the inner product of our features on our edges and the weights, the sort of maximal matching in this graph is equal to the correct bonding pattern of our cysteines. And we can actually formulate this as a loss. And so here, I'm going to call L of y and y hat sort of the number of disagreements in the matchings. And then our loss, this is kind of a generalization of the SVM. And what we have is that we want you get penalized for sort of how many mislabelings you have, and you want your dot product with kind of the correct labeling, that's the term on the far left, to be much, much larger than the product of the weights with any incorrect labeling. So that's what that loss is getting at. Okay. So those are kind of the examples. So now I want to talk about, okay, how do we actually minimize problem? How do we actually solve the optimization problems that these things give? So this is just a reminder, this is what we're solving. And so we've just seen two examples of loss functions that we care about. So the simplest way to solve problems like this that we've all seen is gradient descent. So we have our function f of w, we take the gradient of the function, we want to minimize it, so we just go down the slope of the gradient, follow the negative gradient down. And if you do that, you're going to minimize the function. Now, we have this problem that it's, in the cases we care about, it's sometimes expensive or tough to compute this empirical expectation, right? Sometimes we don't even know the distribution when it's just the expectation of the loss. And sometimes n is very, very large, so we don't want to compute it. So instead what we do is we just choose a random example, we take the gradient with respect to that example, and go in that direction a little bit. So if these are the level curves of your function, you get some kind of behavior like this. You sort of randomly jump around for a while, and eventually the noise averages out, and you kind of go to the middle, go to the bottom of the function. Okay, so if you had parallel computation available, the thing everybody knows that we should do is use that parallel computation to get a lower variance estimate of your gradient. So everybody kind of knows we should do that, right? Or at least it seems intuitive. If you get lower variance, you're going to actually follow the curves of your function much better, and that's going to be a good thing. So a picture of that, right? So here's the level curves for our function. If we have sort of, you actually observe the gradient, it points straight down. And as sort of this number of samples m decreases, you know, we get more and more noise, and our gradients, maybe they're unbiased, they point in expectation in the correct direction, but they sort of, in general, don't exactly point the right way. Yeah, so everybody kind of knows we should do this. But there's this problem, and that's that this only actually works for smooth functions. So reducing your variance only works for smooth functions, but there's a lot of non-smooth problems that we care about. Classification, the hinge loss, the SVM is non-smooth. Robust regression problems are non-smooth. We have a least median loss, so there's a point there where it's non-differentiable. And this structured prediction problem, which was, I guess you could, which in our case was the protein structure prediction, but it also applies to parsing, ranking problems, things like that. That's wildly non-smooth, and I defy anyone to actually give me a smooth version of this that's efficiently computable. Because this set y is the set of all possible matchings on the graph, say. So the techniques we have don't actually work. And the intuition for why they fail is because the gradient, I guess the gradient of a non-smooth function, a function with a kink, is not a good indicator of the global structure. So think about just the absolute value. You take the gradient kind of far away from 0, and it tells you go down quickly, which is what you want. But if you take the gradient close into 0, it still tells you to go down very quickly. And that actually isn't helpful at all. But we have lots and lots of computation available, I've said, so what can we do? And the sort of central idea of this talk is it's a very simple idea. It's just, well, instead of asking for the gradient at one point, we're going to ask for gradients at a lot of different points. So I have my point that I care about, say here. I'm just going to sort of shotgun blast points around that and ask for gradients at all of them. And the intuition here is that I'm going to get some gradients, I guess in this example, on the right side of the point where I care about, some gradients on the left side, and they're going to average out and give me something like a smooth function. And that's going to give me a bunch, and sort of doing gradient descent on that is going to give me a much better global picture of what of what my function looks like. So a little more in depth. So what's the algorithm? Basically, the standard approach is to sample x at random and take a subgradient step for that example, for that sort of element of our data stream. Our approach is, instead of asking for the gradient at the correct point, we're going to just add random noise. So what it looks like is we add a sort of ball of random noise. Our gradient point's actually a little more in the correct direction, we hope. And as time goes on, we're going to decrease the amount of noise we add so that we don't keep just shooting randomly all over the space. And the nice thing is that sort of after a little work, you can actually show that this does the right thing. So the theoretical results we get are, if we're using m gradient samples, sort of m amounts of parallel computation to compute our gradients, for non-strongly convex objectives, we get a convergence rate which is sort of 1 on t plus 1 on square root t times m. So every additional sample, we get a linear improvement in our convergence rate. So if we have lots and lots of parallel computation available, we're going to see exactly the same amount of improvement in convergence. And for strongly convex objectives, which are things like the SVM problem with regularization that Duchi talked about, or other things like that, we get essentially the same result, except we can solve it more quickly. And these are optimal. They're not improvable. You can't do any better than this. At least the terms in red are optimal. You can't improve them. So somehow that's pretty satisfying, because now we have this algorithm. All we need to do is add random noise. It doesn't matter what the function is. We don't, I mean, it has to be convex, I guess, but we don't actually care about the structure of the function. We never really need to know it. Our algorithm is completely oblivious to it, and it's going to get results that are as good as possible. And just one remark on distributing. So sometimes communication costs can be expensive. You know, if you're, I mean, even if you have just one computer with a lot of cores, communicating between the cores can be sometimes expensive. And so the way to get around that is to sort of increase the amount of computation each core does, kind of increase the batch size for each individual core before you actually communicate to some sort of more central processor. And then the hope is that and as long as the computation on the core sort of swamps the amount of communication you're doing, then you're going to still get the optimal convergence rates. So you're going to get an improvement which is linear in the amount of processing power you have. Okay? So yeah, I'm just going to finish up by talking about a few experimental results just to kind of give you guys a flavor of what we've got. My first result is completely simulated. It's just sort of checking, okay, did we do the analysis right, or are we missing something? Because there were those leading terms that I kind of brushed under the rug earlier. And this is solving a robust regression problem, an L1 regression. And this black line in both of these plots is the amount of time we predict it's going to take us, right? So if you look at the bound, thanks. If you look at the bound of here, right, if n gets large enough, eventually sort of the 1 on t or 1 on t squared terms are going to dominate. And so this is just showing that plot, sort of saying, well, as the number of gradient samples goes to infinity, sort of we start to see, you know, we get less improvement for parallelizing. Eventually we get to sort of just the deterministic rates. And I didn't actually show the exact algorithm we ran, but there's clearly some parameters in the algorithm. One is the step size that we're taking, gradient steps with respect, and one is the amount of smoothing we're adding, because we're adding random noise at every iteration. And what this plot shows is sort of, I'm going to run our algorithm for 2,000 iterations on a problem, and I want to see sort of what its optimization error is at the end, depending on sort of the step sizes I use and how much random noise I'm adding. And 1 over u here corresponds to the amount of noise, and eta corresponds to the step size. And what you can see, there's 4 orders of magnitude in that picture. So I'm going off by a factor of 10 to the third and 10 to the minus 1 on each of them. And basically in a huge region of that space, I'm getting to within, like, say 10 to the minus 2 of the optimal value of the problem after just 2,000 steps. So yeah, these things are essentially bomb-proof. You kind of can't mess them up, which is, I don't know, somehow satisfying. And then just a few more things on more real data showing that, okay, you know, this actually does work in practice. So this is solving an SVM problem. This is a text classification problem, and these plots show the mean time to solve this problem to different optimality gaps and different accuracies. And the blue line is with a batch size of 10. That's 10 samples per processor. And the red line is a batch size of 20. What we see is, roughly, as the number of sort of processors we have increases, we get improved performance, although it sort of flattens out eventually. It stops mattering quite as much. And just kind of a similar plot, this shows the optimality gap as a function of time for our different algorithms. And this black dotted line here is an algorithm known as Pegasus, which I think is viewed as one of the better algorithms for doing sort of stochastic optimization in these settings. And you can see that ours are better. Even when we're only using one thread, we actually outperform sort of the more classical approaches. That surprised me. I don't have a great answer for why that happens. If anyone has any hypotheses, I'd be happy to hear them. And then we have similar results for sort of larger, more complicated problems. So these are examples of us solving the parsing problem I talked about in the beginning. And this is a fairly large problem. I can't remember the exact size, but the dimension of the weight vector is something like 200 million or 400 million. And each example, of which there are a couple 100,000, each example is like half a megabyte. So this is a fairly large problem that we're solving. But and what we're showing here is sort of what's your optimization error, what's your optimality gap as a function of the number of threads that we're running the algorithm with. And on the left is just optimization error as a function of the number of iterations. On the right is the amount of time. And so the iteration versus optimality gap looks as we would expect. We do better and better, however, the more parallel processing we get. The time is not quite as clean, but eventually having more threads helps. Right, so just to conclude, what I've shown today is kind of the first parallelization techniques to actually solve these non-smooth problems. I think before this, as far as I know, before this work, we didn't know how to do this. We're currently experimenting with some more tasks, with some web and image ranking tasks, and with some biological tasks like the protein structure prediction problem. Yeah, there's definitely some open issues. One is synchronization. So my algorithm here requires a lot of synchrony. All the processors have to be sort of in lockstep for this to work. And so there's some clear questions of what happens if we don't want that, or can we speed things up? Yeah, and I should just acknowledge all my collaborators, and thanks for your attention. I'll take your questions now.
Thanks very much. Questions? I had a question. Is it clear that the sort of worker central node paradigm for the actual hardware and I/O is the right one, and not some sort of hierarchical thing, in the sense that you can imagine workers working more locally and other ones working in other parts of the space?
Yeah, I don't know exactly the answer to that. So some work I did with Alec, who talked yesterday, who doesn't seem to be here, works on actually having kind of independent workers doing things and then periodically updating a master or somebody who holds some kind of main view of the state. And it turns out that those algorithms still work and you can get performance benefits, provable performance benefits from them. Whether that exactly applies here is not as clear, I don't know.
So show some comparisons for work with the Pegasus, with just n equals to 1, which is pretty much the 0 set, right?
Yes.
So there are outcomes. I guess the explanation might be that if n equals to 1, then your optimization error is of order 1 over t, or 1 over t squared, right? This is for strong convex optimization.
It's for strongly convex, yeah.
Yeah, so optimization error is of order 1 over t squared for the announcement part. The first one you run.
Maybe I misunderstood.
Plus order 1 over t.
Yes, right.
So the first one is 1 over t squared.
Yeah.
But for Pegasus, the first part might be 1 over t. So I guess that's why it outperforms the Pegasus.
Yeah, it could be.
N equals to 1.
It could be.
But I have a question about if n equals to 1, then why you show that the reason why the smoothing works is that it average out all the celebrities. But n equals to 1 still has the average effect.
Well, you're not going to, I guess so, that's a good question. You're not going to get the averaging effects for the sort of immediate function that you're observing, but sort of from a more global perspective, the actual expected function that you're minimizing is going to enjoy the same averaging effects. It's going to enjoy the smoothing effects. And so it doesn't really matter if you do a lot of them at once or do them more over time. Does that answer the question? Is that clear?
Thank you.
Okay, let's thank our speaker again.
I'm going to talk about some new techniques. I guess they're about maybe a little more than a year old now, for solving non-smooth stochastic optimization problems. This is joint work with Peter Bartlett and Martin Wainwright, both faculty here. Right, so I guess just before I start, I want to sort of make like sort of a philosophical statement about solving statistical problems. One is as the number of data points n, that's my number of sort of samples I have available, goes up, my performance should always increase if I'm solving a statistical problem, right? Even with a fixed amount of computation. And my other thing is that as sort of the number of processors I have goes up. As sort of my amount of computational ability goes up, my performance should always get better. I mean, you know, I could always just throw away more accurately predict the structures of these proteins. So this is another kind of prediction problem that we might want to solve, where the data is basically these strings of amino acids. Another one, parsing. You know, this is really useful for, say, like machine translation and things like that. We're given a sentence, the man took the book. We want to fit it into a parse tree. So our data is sort of the man took the book. What we want to do is predict kind of the optimal parse. Separate a sentence into its noun phrase, its verb phrase, and its other constituents. So how do we formulate these as problems, as stochastic sort of or statistical optimization problems? That's kind of our goal in the next couple of slides, is just to construct a loss that measures our performance on these different tasks. So how they can work in sort of parallel computational settings, and then I'm going to finish up with a couple experiments, just sort of showing what they do. Okay, so the sort of smallest description I can give is that I want to solve the following problem, which is to minimize a function subject to some constraints on a parameter vector W. But in my case, in the problems I care about, I'm going to say that the function f is either some kind of empirical expectation, an average of a lot of different functions on data xi, or it's just some expectation of some loss, capital F, where I'm getting samples x from some distribution I don't know. You know, they could be coming in streaming, I could be Google, and I keep getting searches, and each search gives me a little bit of data when somebody clicks on something. So this is the setup. So a few examples. One would be sort of text classification, right? We have documents. We want to decide whether a document is about sports or economics or technology or government or medicine, something like that. Another example that I think is kind of neat is protein structure prediction. So in this, we're given basically we're given a protein, which is a list of amino acids, and we want to figure out what the structure of that protein is, because doing that can sort of tell us how it's going to interact with drugs, things like that. And one thing that helps us be able to predict protein structures is if there is one amino acid called a cysteine. And if we can tell, and cysteines bond with each other, and if we can tell which ones are bonded together, then we can get data if I can't handle it computationally. So I should always be able to improve when I get more of one resource or another. But that hasn't always been the case in a lot of work. So what I'm going to do today is kind of deal with the second point, which is I'm going to talk about sort of how we parallelize stochastic optimization and different learning algorithms. And some of the techniques I show, these randomization techniques, are going to allow us to parallelize sort of previously, I say impossible, we didn't know how to parallelize these things before. So I'm going to start off by just describing my problem, giving a couple examples to hopefully motivate what's going on. And then I'll talk about the algorithms that we develop, and then I'll show how to make them distributed and